Okay, so in this video, we'll just briefly discuss the material in section 2.3, which just tells us, talks about just techniques for evaluating limits. And it's really quite useful because before, we've been evaluating limits partially by creating a chart or a table, and then just looking at how the trend of the numbers to see if we can estimate or maybe try to detect a limit or to, evaluate a limit by just looking at a graph. That's not always the best way because maybe we're not reading the graph right, or the graph just isn't really that precise, or maybe we're still not evaluating. When we're evaluating a limit, we're not evaluating enough numbers really close to the actual limit. Or maybe the limit is like a square root, maybe the limit's the square root of 2, and so a chart can't really tell you that, or a graph really can't tell you if the limit is like an irrational number, or like 0.1008, something like that. When it's that precise, we can't tell. Okay, so here's just a few basic facts. So let's say we're taking the limit of a constant. Okay, so the limit as x goes to c, and let's see if I can make this a little bit bigger. It's hard to see. Yeah, that's a little bit better. So let's say like we're graphing the limit. We have this function y equals k. So if we actually graphed it, it would just be a horizontal line. And so the limit of a constant is just a constant. Okay, so then in 2, okay, so x, if you graph that, that's a straight line, going at a 45-degree angle. And you can just substitute c, the limit, that's a continuous function. There's no holes in it. So the limit as x goes to c of x is c. Again, here you can just substitute like mx plus b. The limit as x goes to c. Again, that's just a continuous function. It's a straight line. And as x gets really close to c, the limit goes to mc plus b. And so we can just use that fact. We don't have to graph or create a table. And now here's another important function. So the limit of the sum is the sum of the limits. And we'll use that later on. So the limit of, let's say you're taking the sum of a function, f of x plus g of x, you can actually evaluate the limits individually. So that'll be quite useful. And then also the limit of the number 5 there, the limit of the product is the product of the limit. So if we know that the limit of f of x is L1 as x goes to c, and the limit of g of x as x goes to c is L2, then the limit of their product is L1 times L2. And the same thing for the quotient, though we're assuming that the limit as x goes to c of g of x is not equal to 0. So of course, if it's 0, then you can't evaluate the limit. So the limit of the quotient, look at number 6 there, is the quotient of the limits. And so here's just another one. Here's just another important fact. So it's this power rule. So the limit of f of x to the n. So we can actually pull the limit inside the exponent. Okay, so we can actually apply the exponent to the limit. So, it kind of looks obvious, but if you actually proved it, it's really actually not very easy to do. Okay, so here's one where, so let's just look at this example. We have a quotient, a polynomial over a polynomial, x squared minus 5x plus 6 over x minus 3. Now you could, factor that and just simplify, but it's the limit is the limit as x goes to 1. Well, the limit of the denominator exists, it's -2, and the limit of the numerator exists. You just substitute x equal to 1, and so you get 1 minus 5 plus 6, and so you get 2 over -2, and so the limit. So in this case, that was kind of a nice use of the limit of the quotient rule. So here's just a few rules that that we'll talk about here. Okay, so like here, in this problem number 1 we just looked at, we just used direct substitution. Okay, the limit of x squared minus 5x plus 6 divided by x minus 3. We're taking the limit as x goes to 1. So we tried direct substitution and we didn't run into any problems. We're not dividing by 0. We're not trying to take the square root of a negative number. So that's actually our favorite kind of limit to find, where we can just do direct substitution. Now we're going to start talking about derivatives, like when we take these difference quotients, it turns out what happens is the denominator is 0. So we have to use some kind of trick. But if you can just use direct substitution, which actually we're not so lucky for the most part in calculus in doing that, that's what we try to do. Okay, so then there's that number 2, but this is what we kind of did in the previous sections. We're trying to find the limit from a graph or a numerical approach. You can estimate the limit, but it's only by luck is it exact. Because let's say the limit is the square root of 3. You're not going to be able to tell that from a graph or from a numerical approach, or maybe even the limit is a rational number, but you have to take the graph the function changes really fast. It's growing really fast. You have to get really very close to the number you're taking to the limit. Maybe you're not evaluating numbers that close. So I think using a graph or a numerical approach can kind of give us an idea, but it's not it's not the best way to do it. It's not the most satisfying way of evaluating a limit. And then there's the algebraic or analytic approach, which we're going to have to do when we start talking, when we do difference quotients, like f of x. What do I mean by difference quotient here? Let's see if my pen works. Here's what I mean. We try to take this kind of limit. Over f of x minus f of h See, in this case, the denominator is 0, so you can't actually use that direct substitution. So these difference quotients, there is usually not usually, for the problems in our class, there's a finite limit. And so you usually have to do some kind of algebraic trick. Let's just go on here. Let's see how we can do this. So, well, like right here. So let's look at example 2 there. Well, again, now let's try. Our favorite rule is direct substitution. Yeah, we want direct substitution. But okay, so well, 0 in the numerator is okay, but look what happens. When you do direct substitution, problem number 2, x squared minus 5x plus 3 divided by x minus 3. Well, what happens is that, well, you're dividing by 0, so that's not okay. That doesn't mean just because you get 0 over 0. So that doesn't mean that the limit doesn't exist when you have 0 over 0. It just means that you can't evaluate the limit by direct substitution. So, okay, well, this problem is set up nicely, and we factor the numerator into polynomials of degree 1. X squared minus 5x plus 6 is x minus 3 over x minus 2 divided by x minus 3. Yeah, so x minus 3 drops out. So it's the same as the limit so we end up evaluating the limit of x squared minus 5x plus 6 divided by x minus 3 is identical to the limit of x goes to 3 for the function x minus 2. So it just is 1. So even though the function, again, look at that function, x squared minus 5x plus 6 divided by the quantity x minus 3. It's not defined at x equal to 3, right? Because you're dividing by 0, but its limit is still 1. If you actually graphed it, as x goes to 3, the y coordinate goes really very, very close to 1. So you might try graphing that on your graphing calculator. You should see that as x goes to 3, the graph goes very close to 1. Okay, so now here's one. Okay, so this is kind of you probably have seen this, I think, in I can't remember which section, but in some of the earlier sections, they had problems like this. Okay, let's look at example 3. So, so it's this difference, you're taking a difference in the numerator, square root of x plus 2 minus the square root of 2. Okay, well, that's defined at x equals 0, it's 0. Okay, but the denominator, once again, is 0. Okay, well, that's not good. And then, we get 0 over 0. So again, 0 over 0, the limit may or may not exist. So what the typical trick is that when you have like this, like you have the square root of x plus 2 minus the square root of 2, we're going to multiply. Usually, you probably in your previous algebra course, you learn how to multiply by the conjugate of the denominator, but we're going to multiply by the conjugate of the numerator. And that will get rid of the square root in the numerator. Do you see, this is the conjugate, this part right here. The square root, so the original numerator was the square root of x plus 2 minus the square root of 2. And the conjugate is the square root of x plus 2 plus 2. So we're just using that famous rule, a minus b. I know it's hard to read with my, I think this is okay. So we just use that rule. And so the numerator turns into x plus 2 minus 2. So we just end up with getting x in the numerator. Oh, and the x's drop out, right? So we have x in the numerator, denominator x times what turns out, of the conjugate. So we end up taking, so we end up taking the limit as x goes to 0, 1 divided by the quantity, square root of x plus 2 plus square root of 2. And it turns out to be 1 over 2 times the square root of 2. And again, so if you graph this, let's look at example 3. So like trying to estimate that from a graph or a table, but you're never going to, I mean, I'm not you, I'll include all of us, me too. It's not just you, okay? If you, it's just to estimate, to determine that the limit is this irrational number. An irrational number is like that square root just goes on and on forever. It's not a finite number of decimal points after the, it's not a finite number of digits to the right of the decimal point. Okay, but once again, the original function, we're taking the limit as x goes to 0, square root of x plus 2 minus square root of 2 over x. That original function is not defined at 0, but the limit is equivalent to taking the limit of this original function is equivalent to taking the limit of this. After, of course, after we do some algebraic trick. Okay, so 4, again, you're taking the limit as x goes to 4. Again, the function's not defined because we're dividing by x minus 4. Well, let's just simplify the numerator. Of course, what we always learn in our algebra courses, let's find a common denominator. So we, the common denominator of the numerator is 4x. So we just we multiply the numerator and the denominator by the same, basically we're multiplying by 1 in the form of 4x over 4x. And then we simplify, and it turns out x minus 4 cancels. Just be careful. In the denominator, you have x minus 4, and then in the numerator, you have 4 minus x. So you have to multiply, you have to factor out a -1. So yeah, so this is what we get right here. So when you cancel factors of x minus 4, there's actually a minus sign there. There's a negative. So it turns out kind of, who would ever think that these are kind of equivalent? So this function right here, taking the limit of that function as x goes to 4 is equivalent of taking the limit of this function as x goes to 4. And it turns out to be 1 over 16. So again, the original function is 0 over 0. But if you actually graph that function, if you actually graph this function right here, as x goes to 4, the y coordinate is going to go to a minus 1 over 16. Okay, so that function goes very close. The graph goes very close to the ordered pair 4 common -1 over 16. And so let's see here. Tell me a little bit more. Okay, so let's say that, so here you have like a piecewise linear function, and again, it's not defined at well, there's actually a hole in the last one at x minus 1, but in this case, it's not really a problem because the function, the part where this last part where there's a hole at, it's not defined at x equal 1. Well, but the domain is x greater than 2. So in this case, you can actually use, for many of these, you can use just direct substitution. Like the limit as x goes to 1 from the left. Well, it's just direct substitution, right? You're looking at the limit as x goes to 1 from the left, right? So you'd be looking at this part of the function, right? Here's kind of my kind of crummy graph right here, but it would look kind of something like this. So like if this was x equal -1, there'd be a hole right there. Okay, but yeah, but it's so, but that function is defined for x to the left of x. It's defined for the left of x equal -1. So again, you can just use direct substitution, and then if you plot from the limit as x goes to -1 from the right, okay, well now you have to use the fact that the graph of the function is like is +6, something like that. And then, okay, so when you're coming from the right, it's 6, the limit is 6. And when you're coming from the left towards -1, you just plug it in. And you get the answer is 4. -3 times -1 plus 1 is 4. Okay, but the problem is, see how, like, look at C. Remember that D and E means does not exist. Okay, so when you're coming, the limit as x goes to -1 from the left is 4. The limit as x goes to -1 from the right is 6. So the overall limit doesn't exist, right? So an actual limit as x goes to -1 can't exist unless the limit is the same as we go from the left and as we go from the right. And so some of these other ones we can actually, but look at here. So, but as you go towards x goes to 2 from the left or from the right, you still get the value of 6. Okay, because we can actually substitute. So if the limit as x goes to 2 from the right, we can use direct substitution because 2 is in the domain. So for x greater than 2, as 2 goes to that last function, x plus 4 over x minus 1 from the right, well, that function is defined for x greater than 2. So as you go from the right, we can just use direct substitution. So in this case, the limit from the left and the limit from the right is 6. So in this case, the limit exists. So we're almost done here, students. So if we were in class, I'd probably be telling everyone not to look at their cell phone. Okay, anyway. But now I have no idea. Okay, so okay, so then the famous squeeze theorem, which, okay, now students, this theorem here, yeah, so we talk about this in Math 250. And this is a theorem for, a skilled mathematician. So let's say if you were a math major and went to graduate school and you were going to become you wanted to, do research in mathematics. This is a theorem you would definitely use, maybe, I don't know, not definitely use, but it'd be, this is what this theorem is for. It's for people who are doing research. Okay, and we're actually going to. I don't think it comes up too many times in the course. I don't think I've ever. I don't know if any teachers ever in a Math 250 course use this on a course. I shouldn't say that. Maybe they have. I haven't. But basically, it's saying. So let's look at this. So look at that graph. You have the graph of g of x is above. That's the one in the black ink. G of x is above f of x. H of x, which is in blue, is below f of x. And they all agree, and they all intersect at point C. All those three graphs intersect at point C. And so what it's saying is, so we know that the limit of h of x, and that's the one that's below f of x, goes to L as x goes to C. And we know the limit of g of x as x goes to C, also goes to L. Remember, g of x is the one that's above. And so what the squeeze theorem says, well, f of x, since f of x is in between g of x and f of x, and g of x goes to L as x goes to C, and h of x goes to L as x goes to C, f of x also must go to L as x goes to C. It's kind of squeezed in. So, okay. So, and the reason we talk about it, I know it comes up a couple times in some of the proofs and problems. There is this famous, this theorem right here is two special trig limits, especially that first one, sine of theta over theta. We know that sine of theta, at theta equals 0 is 0, and of course theta itself is 0. It's 0 radians is 0, but their quotient, if you actually graphed, like try that on your graphing calculator, try graphing this function right here in your graphing calculator, and it should approach 1 as as theta goes to 0. Now that's a fact you'll use a lot, or not a lot, but it's sometimes in the course. At some point in the course, it comes up. And the other theorem is also that other quotient is that other limit is also used. But I think sine theta over theta we see a lot more. Now, students, I am not going to prove this theorem right here in this lecture kind of video. If anyone is interested in how to prove that the limit of sine of theta over theta as theta goes to 0 is 1, let's just meet up in Zoom and we'll do it live. I think that's a lot easier. The only one thing I'll say right here is that like the area of this sector right here, and we're talking about, see, it's a little even hard to tell by this picture right here. So we're talking about the area of this sector. We're just talking about, so if this is theta, so what's the area of this part of the circle? And we know the area of the whole circle. In this case, r is 1. So in this case, r equals 1. It doesn't look like an r to me, but okay. So the radius is 1. But you know that, so if the radius, so we know the general area, we know the formula for the area of a circle is pi r squared. If r is 1, we know that the area is pi. And okay, so the area of the circle of radius 1 is pi. And so we know the area of and so what part of the circle do we have? Well, so it's theta radian, so it's theta over 2 pi. That's the portion of the circle that we have. So the area, so if we just go theta radians, the area of the circle is theta over 2. So okay, and if we were considering, if it was a general circle r, it'd be theta r squared over 2. Okay, so you don't have to know that, and you don't have to know the proof of this theorem. There's no proofs on your test. Even if it was like if I was testing you at school, I wouldn't do that either. But if anyone wants to go, let's say you love math and you like proofs, and if you are a math major, yeah, I would. If you're an engineer, knowing the proof of this is really not that important. But not saying you might not find it interesting. If you are a math major, definitely. So if you're a math major, I would, this is something you should want to know how to do. Okay. Okay. So, okay here. So let's look at problem B right here. So, okay, well, you want to look at the limit of, if you see here in the notes, first of all, students sometimes make mistakes. They try to evaluate this limit by using this false formula right here. Sine of ax is not equal to ax. So sometimes it's a little frustrating. I give like a problem like B and the students get the right answer, but their work is wrong. And so I mark it wrong, even though they end up getting the right answer. So what some students try to do is just pull that 2 out of sine 2x, and you really can't. So what we have, when we evaluate this limit, we need to get it in the form of sine of 2x, and we need to get a 2x in the denominator. Okay, so you notice what we're doing right here. Oh, there's a 2x inside here, inside sine of 2x. Multiply the numerator and the denominator by 2, and now you have like this original function sine of 2x over 5x is the same as this function right here. Right, so it's the same as 2/5. No, it's pretty bad. It's the same as 2 over 5 sine. This is how, remember, we're going to use that formula. We're going to use that limit, the sine of x over x. So now we have sine of 2x divided by 2x. And as x goes to 0, this part goes to 1. Right? So a lot of students get this problem correct. I mean, they get the right answer, but their work is wrong. So it's kind of frustrating problem for a lot of students. Okay. And then again, the tangent of x over x also just turns out to be 1, right? Because, and again, we're just using some kind of algebraic technique here. But again, if you actually evaluate it, tangent of 0 is 0, right? Tangent of because it's sine of x over cosine of x. So the tangent of 0 is 0. So this would really be another one of these 0 over 0 if you did direct substitution. But if you do some kind of algebraic trick, use the trig substitution. Oh yeah, well the tangent function is defined as sine of x over cosine of x. So now we end up a limit of tangent of x over x. Oh, it's the limit of 1 over cosine times sine of x over x. And we know that sine of x over x as x goes to 0 is 1. And cosine of 0 is 1. We can just use direct substitution. So again, you just have to use some kind of algebraic trick. And again, the same thing as D. You want to get in the form of something like sine of x over x, or you want whatever you're taking the sine of, you want the numerator, you want the denominator to be the same thing. Okay, and here we're just using we're kind of using the reciprocal. We're just using the fact that the limit of also, you can actually, the limit also applies, that the limit of as x goes to 0 of x over sine of x is equal to 1. So that's what we're using there in D. But notice that you get it, notice just by using some, you like in D here, factor out 2, right? And now the numerator, we're taking the sine of the numerator. So the limit of x minus, so we're taking the limit as x goes to pi.
Unknown caller.
Oh, that's not the right student, sorry. Yeah, sometimes people call me up. Okay, so not too often. Okay, so and then so but you see that we're getting the limit in the form of 0 over 0. Okay, but we're taking the sine of x minus pi, and what's in the numerator is x minus pi. So as x goes to pi, it's 0 over 0. And so that part just goes to 1. Okay, so here, so there's a few other problems that I'll let you read yourself, but just contact me if you want to if you want to talk about that. Okay, so some of these problems that I haven't talked about. Okay, this is the one last thing. You might have to deal with one-sided domain. So if you're taking the limit, is x, the limit, so here we have this function, the square root of x minus 1. Okay, and so the limit is 0. Just be careful. You can only take the limit as x goes to 1 from the right. So if you take the limit as x goes to, let's say you're taking the limit as x goes to 1 from the left of the square root of x minus 1, it doesn't exist, right? Remember, DNE means doesn't exist. And so the limit as x goes to 1 of x minus 1, you have to restrict the domain. Because when we say the limit as x goes to 1, that means we're going either from the right or from the left. And it doesn't exist. It only exists as we go from the right. And so I'll let you try some. These are some more problems right here that you can try. So again, here, like in 5, the correct way to do it, again, here's the common error that students do. Let's see if I can do this, of course. Hello, what happened? Okay, so here's the common error that students do. They'll go 2, and so I'm just saying this is wrong. They're not equal to each other. But see, then when you take the limit in this case, you're actually not taking the limit as x goes to 0. So you actually could use direct substitution. This is what I'm talking about right here. So sorry, I misread the problem. But let's say you're doing this. Sine of 2x over x. What a lot of students will try to do is say, this is equal to the limit as x goes to 0. Oh, now they're going to just directly pull out that 2. Okay, so now, and we know that the limit of sine of x over x as x goes to 0 is 1. So you get the correct answer if 2, but the problem is that this is not equal. Yes, sine of x, don't do that. Don't do this, students. Let's see if I can write it so you can actually read. Sine of 2x does not equal 2 sine of x. Okay, I think I'm just going to stop right there. And if you have any questions, we can just contact me via Zoom.